Variable type and classification is incredibly important in the field of statistics because it allows you as a researcher to determine what methodologies are appropriate as it pertains to your data. Only certain methodologies can be applied with certain variable types are present. So in this video, I hope to discuss variable types and classifications with you and hopefully make clear what measurement scale is being utilized for certain variables, what type of variable, and whether a variable can be continuous or discrete. So we have two types of variables. Those variables are qualitative and quantitative. Quantitative can either be continuous or discrete. So qualitative variables can be remembered as being categorical. And there are two measurement scales as it pertains to qualitative variables. Those are those are nominal and ordinal. So nominal and ordinal are our qualitative type variables. Quantitative are countable values, so numerical, and they can be either discrete or continuous. Measurement scales for these type of variables are interval and ratio. So as far as quantitative variables are concerned, they're sometimes referred to as numeric variables. These are variables that represent a measurable quantity. Examples include number of students in a class, number of square feet in a house, population size of a city, age of an individual, height of an individual. Again, these are countable values. Now, as you recall from a prior slide, qualitative variables are sometimes referred to as categorical variables. So these are variables that take on names or labels and can fit into categories. Examples might include eye color, gender, breed of dog, level of education, marital status. And you can see in each instance, we're looking at various categories of a variable. Now, continuous variables are a quantitative type. A continuous variable is a variable whose value is obtained by measuring. It can take on an uncountable set of values. All right, so these values can be counted infinitely. Now, this might fly in the face of pragmatic rationality and logic, but just bear with me. We'll go through a couple of examples and hopefully that'll clear some things up. So depending on the type of continuous variable, zero may be arbitrary or not arbitrary. And as you recall, interval and ratio variables are examples of continuous type variables. So here's some continuous variable examples. These are, again, variables which are quantitative, they're countable, and they can go on infinitely. All right? So height. All right, now I know what you're thinking. Height of a human being at a certain point, your body becomes structurally unsound. The same is true for weight. Enough weight and your body will break down and become completely gelatinous. But in the case of our particular textbook definition, we're going to imagine that, maybe there's some sort of genetic modification that can be done where weight can exceed what the physical limitation is for the human body. Same for height. All right, so you have to think in terms of the definition, not so much in terms of objective reality, okay? So height, something can be infinitely tall, and weight, something can be infinitely heavy, all right? Miles per hour, again, there's certain physical barriers perhaps for certain automobile types, but in this case, we're going to imagine that somehow or another, a particular automobile perhaps can be modified in some way, or maybe the road in which it travels, the friction can be reduced, and it can exceed which we would normally expect to be the physical limitation for that automobile. National debt is an easy example of this, as far as existing both in the textbook example and in objective reality. And runs scored in a baseball game. Again, this is another example where you might think, okay, at a certain point they'd call the game, but from a theoretical perspective, if they don't have a mercy rule in place and runners continue to hit and not either fly out or be tagged out or ground out for that matter, or strike out, then the game could theoretically go on and on. Again, we're looking past the fact that, players would age, injuries, etc. Theoretically, you could score an infinite number of runs in a baseball game. A sport which has a timer like football or basketball, obviously, a continuous variable as far as points scored may not be applicable. Discrete variables are also quantitative variables. Remember, quantitative variables can either be discrete or continuous. All right, and these are countable values. A discrete variable is obtained by counting, but in this case, there is a limitation. Discrete variables have a limited set number of possible values. Interval and ratio variables are example of discrete types of variables. They're measurement scales, interval and ratio. So here are some discrete variable examples. And again, these are finite. Gallons of gas in a Ford Focus, assuming that the gas tank isn't modified in any particular way. The gallons are standard as they come out of the pump, and the amount of the volume that the particular of gasoline that the car can hold in its tank is set amount. So if it's a 16-gallon tank or a 12-gallon tank, it can only hold 12 gallons or 16 gallons or whatever the amount may be at a particular time. Number of standard pencils in a mug. Again, we're assuming that we're not in any way doctoring the size of the mug where the pencils are applying some sort of chicanery as it relates to maybe slicking the pencils up. We're going to assume that that is a finite number that can fit in a certain pre-selected mug, certain pre-selected pencil type. Letter grade for a class, assuming that it's a class that doesn't offer extra credit or anything like that, we can only go between A plus and F. And if there's an underlying numerical value for that, it would go between 0 and 100. Number of quarters in your couch, assuming that we're using a certain tender from a certain nation state. So we would say, US quarters, year 2007, the couch being a certain pre-selected couch type. We're assuming that this value would be discrete. The couch isn't going to change in size. The quarters aren't going to change in size. Only so many quarters can fit in that particular couch. Now, out of all of these examples, probably the two that are most definitive as far as giving a fair and clear definition to this concept are probably gallons of gas, because the measurement is not going to change, and letter grade for a class, and that the scale is not going to change. And here's a better way of visualizing perhaps measurement scales together in a single slide. As you can see, ratio and interval are both quantitative, and they can be continuous or discrete. Ordinal and nominal are both qualitative, and they are neither continuous or discrete because they're categorical. Remember? So ordinal and nominal are qualitative scales, categorical, okay? And ratio and interval are quantitative scales, meaning they can be counted, and they could be continuous, meaning that they go on forever. They are an indeterminate amount of countable values, or discrete in that there is a set limit. And some examples here are for ratio are occurrence. So if we're counting how many carbs an individual consumes in a day, that could be ratio because a true zero exists. We'll get more into this in the subsequent slides. Interval data, no true zero can exist, meaning that if we're measuring temperature and we have 0 degrees, that doesn't necessarily mean the absence of temperature. It just means that 0 degrees is the measurement, whether it be 0 degrees Fahrenheit or 0 degrees Celsius. Ordinal is categorical rankings, in this case, letter grade. And nominal is categories, but no ranking. So in this instance that we have as far as example is concerned are gender and race. And we'll go into this in later slides. So here are more examples of types of variables. For qualitative categorical, we could have marital status, are you registered to vote, eye color. These are defined categorical groups. And for quantitative, which is numerical, we have discrete, number of children, defects per hour, counted items, and continuous is measured characteristics, which again could be counted infinitely. And also, as a reminder, for our quantitative variables, they could either be continuous or discrete. And as far as measurement is concerned, they could be, again, this is for quantitative, they could be ratio or interval. As far as qualitative is concerned, those variable measurement scales will either be nominal or ordinal. All right, and we're going to talk about scales now. All right, so we talked about variable types, whether those variable types are continuous or discrete if they're quantitative. And now we're going to talk about measurement scale. Okay? All right, measurement scale. There are 4 types: nominal, ordinal, interval, and ratio. And as a reminder, okay, ratio is discrete, interval is continuous, ordinal is neither continuous nor discrete because it's categorical type, and nominal is neither continuous nor discrete because it's categorical, i.e. qualitative. All right, nominal variables. A nominal scale describes a variable with categories that do not have a natural order or ranking. So examples of this are hair color, hometown, gender, cat breed, music genre, diagnosis type, yes, no. If an individual is, say, blonde, brunette, a redhead, blue hair, green hair, gray hair, we're not going to say that one is particularly better than the other. You might have a personal preference, maybe a dating preference as to what you'd prefer, but it doesn't necessarily mean that one is held in higher esteem than the other. So in this instance, think of these as database entries. If we have an individual within a database, maybe we have their gender, their hometown, their hair color, maybe their favorite music genre. They're all in there as selection, but we're not holding one above the other or one lower than the other as far as the categorical designation is concerned. One is not preferable to the other. One is not less than the other. Okay? Even if you have a personal preference. Now, ordinal is similar. However, with an ordinal scale, the order doesn't matter, but not the difference between the values. So in this case, there is a ordering hierarchy. So for an easy way to remember this is for survey ranking. Strongly agree, agree, disagree, strongly disagree. There's a definitive difference between there. We're not talking about hair color or eye color or anything like that. In this case, each one of these prompts, the response differentiates one from the other. Education level, undergrad, postgrad, grad, there's differentiation here. Again, we can draw a hierarchy as well. Household income, similarly. Now, interval variables, as a reminder, are quantitative, meaning that they are counted, where the other 2 types which we had covered were qualitative in that they were categorical. So for interval variables, these are variables which are measured that are used to define values measured along a scale, with each point being placed at an equal distance from another. What do I mean by this? Well, when we think of time or IQ test or temperature, each mark on a thermometer, whether it be Celsius or Fahrenheit, is equidistant from the other. So 1 degree follows 2, follows 3, follows 4. This isn't a parabolic scale where, there's a greater distance, say, between 1 and 2. There's always the same distance between each on our scale. Same is true for time. each second is whether it be 5 seconds between, whether it be, say it's 1 o'clock, and then it's 1 o'clock and 5 seconds, 1 o'clock and 10 seconds, 1 o'clock and 15 seconds. Each count of 5 seconds is 5 seconds away from the prior mark. It's not that if you were to say it's 1:05 and then it being 1:10, that there's a separate countable amount of time which has passed as being distinguished by those symbolic values. All right, so this is just thinking even scale, a ruler. All right, temperature. It's an even scale. Everything between each major marking is equidistant. Now, as it pertains to our ratio variables, all right, our ratio variables are interval variables, but with the added condition that 0 of the measurement scale indicates that there is none of that variable. So as it relates, as this differentiates from our interval variables, for interval variables, remember, we're using a equidistant scale. If we have 0 temperature, that means if it's 0 degrees Fahrenheit, or we'll say 0 degrees Celsius, 0 degrees Celsius means that it's freezing. It doesn't mean the absence of temperature. All right, for time, if 0 seconds pass, that doesn't mean that time has stopped. It just means that 0 seconds have passed. All right, maybe microseconds have passed, or 0 minutes have passed. Maybe we have so many seconds have passed, but it doesn't mean the absence of time. On an IQ test, 0 indicates a certain measurement of IQ. It doesn't necessarily mean that the individual being assessed doesn't exist, or they lack any cognition whatsoever. Ratio is different in that 0 actually is a 0 measurement. So for salary earned over a time period, if you're unemployed, you might earn $0 over a certain time period. So if you're unemployed for a year and you don't earn any money, 0 doesn't mean, it means that $0 were earned. Range of motion, if you can't move a certain body part at all, it could be measured at a movement of 0 degrees as far as the range is concerned. Carbs consumed, maybe you're looking at carbs consumed in a week, you might consume 0 carbs. Right? That doesn't necessarily mean that the whole concept of carbohydrates cease to exist. It just means that you've consumed 0 carbs. Or rate of occurrence within a sample or population. For example, maybe we're measuring cancer in a certain village in the Himalayas. Maybe there's no individuals within that particular village who have cancer. This doesn't necessarily mean that cancer ceases to be. It just simply means that there is no cancer amongst that sample or population currently. Now we're going to talk about lurking variables. Now, lurking variables are, the whole prior slides were about the different measurement scales, types of variables, continuous or discrete, etc. Lurking variables have to do actually with analysis as it pertains to creating models and measuring outcomes. So this is something we're going to talk about more so in other video lectures, but I wanted to introduce the concept now since we're on the topic of variables. All right, so we're moving a bit in a different direction here. So a lurking variable is also known as a confounding variable. It's more commonly known as a confounding variable. However, it could also be referred to as a lurking variable. A lurking variable is a variable that researchers do not include in a statistical analysis, but it can still affect the outcome. These variables can create problems by biasing your statistical results in any of the following ways. All right, so let's pretend that you've done a study and you have your results, whatever they may be, and maybe you've built a predictive model. A confounding variable would be a variable which is present within the phenomenon, but your model that you've built to predict outcomes hasn't taken it into account. So maybe you're looking at some sort of various variables as it relates to outcomes of a student in a particular course, right? Maybe you're teaching a statistics course and you're measuring the students' Maybe it's a graduate level statistics course and you're measuring the student's undergraduate GPA. You're assessing that. You're assessing the school that they had attended prior to graduate school. You're assessing their science GPA. There's many variables that you can assess. However, in doing your and in coming to your whatever your outcome may be, you're measuring academic performance in this case in the particular course that you're teaching, um, which would be graduate level statistics, I suppose. There might be a variable which you did not account for, which is some way impacting your model. All right, so this could be magnifying the real effect. So maybe you think that your variables that you've accounted for are they're really the impacting the outcome, but maybe there's another variable in there that is impacting it instead, and which you see is just coincidental as far as your variables are concerned. So there's something else there that's having a greater effect. Maybe it's impacting your three variables that you're accounting for, or maybe it's just that in and of itself is impacting it, and the other three variables, whatever their values may be, is coincidental. It could weaken the appearance of the relationship. So maybe your model is not providing a it doesn't seem like there's a strong relationship between your variables and the outcome, but maybe that's because there's another variable interplaying somewhere in there that you haven't accounted for. It could change the sign of the correlation. So maybe you have a model built where you think that something is having a negative impact, but it's actually not having an impact at all, or maybe it's having a positive impact, but maybe there's something else in the phenomenon which you haven't accounted for, which is dampening the impact. It could mask an effect that actually exists, or it could create phantom correlations where none exist. So again, just think of this as there's something in the phenomenon which you haven't accounted for in your model that is somehow causing some sort of confusion as it pertains to your model and its ability to predict outcome. So here's a way to remember the lurking variable concept. After the discovery of planet Neptune in 1846, there was considerable speculation that another planet might exist beyond its orbit. The search began in the mid-19th century and continued to the start of the 20th century in the quest for Planet X. It was proposed that the Planet X hypothesis might explain apparent discrepancies in the orbits of the giant planets, particularly Uranus and Neptune, speculating that the gravity of the large unseen ninth planet could have perturbed Uranus enough to account for the irregularities. So as we get to the outer solar system, there are certain orbital irregularities which sort of are not observed in the inner solar system. And this has to do with Newtonian motion, et cetera. And no one's really quite sure why this phenomenon would be occurring, because if the Newtonian motion and the conclusions of such would be a constant, then there should not be any irregularities, regardless as to where the solar bodies are located. So the thought is that there might be something out there, maybe another planet that we haven't discovered, which is some way through its orbit or through its presence impacting the orbits of these outer planets, thus Planet X. So Planet X in this case may be our confounding variable, but obviously there's some confounding variable out there which is impacting our ability to appropriately assess these orbital formations in the way which they currently are measured and perceived. Which brings us to some other concepts which are somewhat related, but and again, we'll get into these in later lectures. Explanatory variables. Explanatory variables are also known as independent variables, or predictor variables. They're abbreviated as IV. And an independent variable is the variable in an experimental study that's going to be manipulated by the researcher. So you can think of this as being the cause. So you're looking at a model with cause and effect. The explanatory variable or independent variable, or IV as it's commonly abbreviated, is the variable which you're looking to see if it is a cause. And then the dependent variable, which we're going to look at the next slide, would be the effect. So does the measurement of the independent variable impact the dependent variable? Does the cause somehow impact, or can this variable be utilized in a system of analysis and methodology to model the effect? So response variable or dependent variable is also abbreviated as DV, is known as the dependent or outcome variable, but it's far more referred to as the dependent variable, just like in the prior slides, the explanatory variable is far more commonly referred to as the independent variable. But in any event, the dependent variable, also abbreviated as DV, its value is predicted or its variation is explained by the explanatory variable, i.e. the independent variable, in an experimental study. That is the outcome that is measured following the manipulation of the explanatory variable. So hang on with me for a second. I have some examples in the last slide. A way to remember independent variable versus dependent variable is the independent variable can be thought as of a cause, with a dependent variable being thought of as an effect. So here's a couple silly combinations to drive the point home. So we're going to pretend we're going to be building some amateur models here to try to assess, to try to build some sort of modeling methodology which has predictive capacity where the independent variable might be able to predict the dependent variable. So in our first instance, number of alcoholic drinks consumed is the cause. Can we create a model in which the number of alcoholic drinks consumed can accurately predict blood alcohol level effect? Can we assess individual hours spent studying as our independent variable? Can we model that and see if it impacts the outcome or effect course GPA, the dependent variable? Packs of cigarettes smoked daily, in this case would be the independent variable. Does that impact lung capacity, the dependent variable? Can we create models in which the independent variable can be assessed in a manner which can appropriately predict the dependent variable? And we'll do this. We'll do this in later lectures. Hours spent training. Does that impact marathon placement? Cause hours spent training, potential effect marathon placement. Does the height of an individual, our independent variable, does the height of an individual potentially impact the number of dunks per season? That being our dependent variable, or DV. So that is it for this particular lecture, folks, this particular video. I hope you learned something. You probably found your way here because you're either preparing to do some research of your own and you need to determine variable type as it relates to applicability of methodology, or maybe you're taking a statistics 101 course and you need to have some further lecture material to help supplement the lectures that you're currently receiving in your course. In any event, this is important because it allows you, as far as determining measurement scale, type of variable, and whether those variables are continuous or discrete, it allows you to determine what methodologies are applicable and appropriate for your research data. And as far as independent variable, dependent variable, and lurking or confounding variables are concerned, that will become more useful as you begin the modeling process, building regressions, etc., which we will do in later lectures. So I know that this was a longer lecture, and I appreciate you sticking with it until the end. If you enjoyed this content, please consider liking and subscribing. It would mean a lot, and it would help this channel out. I look forward to providing you with more useful content moving forward, and I hope that all of your research and your studies and whatever brought you to this video continues to go well for you. Thanks for stopping by, and have a wonderful rest of the day. Take care.